Every year, corrosion alone costs the global economy over $2.5 trillion. Between almost every surface in the built world and the forces trying to destroy it, there is a thin layer of chemistry doing all the heavy lifting. That layer is a polymer coating. Welcome to AetherLab PolyCoatings. This is the series where we break down the science, engineering, and real-world performance of industrial polymer coating systems. Today we are mapping out the entire coatings landscape so you understand what these systems are, why so many different chemistries exist, and how we can choose the right one. A polymer coating is a material applied to a surface to form a continuous protective film. That film is the first line of defense between the substrate and the environment. The substrate could be metal, concrete, plastic, wood, glass, or another polymer layer. The environment is whatever combination of stresses that surface will face: chemical attack, corrosion, abrasion, UV degradation, thermal cycling, or biological fouling. You will find polymer coatings on warehouse floors, inside chemical storage tanks, on offshore platforms, across bridge decks, and protecting vehicle and aerospace components. The global protective coatings market is valued at over $160 billion. This is one of the largest applied chemistry industries on the planet. Every industrial coating is a formulated system. The binder is the polymer resin that forms the film and determines fundamental properties. In a two-component coating system, there are two parts, and the crosslinker reacts with the resin to cure it into a permanent three-dimensional network. Then you have pigments for color and barrier properties, fillers for mechanical performance, additives for fine-tuning, and a carrier, either solvent or water, to make it all applicable as a liquid. In 100% solid systems, there is no carrier at all. The coatings we will cover in this series are mostly all thermosets. That means the resin and crosslinker undergo an irreversible chemical reaction. Once cured, they cannot be remelted or reshaped. That permanence is what gives these systems their superior chemical resistance, thermal stability, and durability. There are other chemistries out there for specialized niches, but following systems are by far the most common across the industry. Epoxy is the workhorse. Exceptional adhesion, outstanding chemical resistance, excellent barrier properties. It is used as primers, floor systems, tank linings. Main weakness include UV stability, so it will need a top coat if applied surface will be exposed to sunlight. Polyurethane brings what epoxy lacks: UV stability and gloss retention, the go-to top coat for exterior applications. A classic system pairs an epoxy primer with a polyurethane top coat. Polyurea is the fast cure champion, reacts in seconds, tough, flexible, waterproof. Think truck bed liners, containment, flooring, waterproofing membranes. Polyaspartic started as a polyurea subclass, but has become very popular in decorative and commercial flooring. Fast cure, good UV stability, bridges the gap between polyurea speed and polyurethane aesthetics. Polysiloxane uses silicon-oxygen backbone chemistry for exceptional weathering resistance. Increasingly used on infrastructure and marine and high-performance top coats, each system has distinct strengths and trade-offs. The art of coatings engineering is matching the right chemistry to the right application. The breadth of industries coatings serve is enormous. Industrial flooring, marine, oil and gas, infrastructure, automotive, aerospace, electronics. Wherever there is a surface that needs to last, there is a coatings engineer who has specified a system for it. How a coating is applied matters as much as what it is made of. Brush and roller for edges and small areas. Airless spray for most industrial work, where a hydraulic pump atomizes the material through a spray tip. And plural-component spray for fast-reacting systems like polyurea, where separate heated or non-heated resin and crosslinker streams mix at the gun and react on contact with the surface. So how does an engineer choose the right system? It comes down to the substrate, the service environment, the performance requirements, application constraints, regulatory compliance, and lifecycle economics. Coating selection is never about picking the best product. It is about picking the right product for the specific combination of factors on that project. So that is the landscape. You now have a basic foundational understanding of what polymer coatings are, the major chemistry families, and the factors that drive system selection initially. In this series, we are going to dive deep into each system. We will break down the chemistry, examine real-world performance, discuss application best practices, analyze failure modes, and also explore how AI and computational materials science are accelerating coatings innovation. Next episode, we will dive deep into the epoxy systems. Like, share, and subscribe to PolyNovel and turn on notifications so you do not miss the deep dives coming in this series. Thank you for watching.